call on you. Dima.
Okay, so I have a question to Zlatko. So thank you for a very good talk. I actually have two questions. One is a minor clarification, and another question is somewhat more advanced. So the clarification question is, what exactly do you mean by rotating the magnetic field? So do you keep the absolute value of the field constant, or you just add a parallel component without changing the perpendicular component? I am asking because the change in the perpendicular component in the first scenario would change the filling factor.
Yeah, we don't want to do that. So obviously, the way we do the calculation is always projected to a lambda level at the fixed filling fraction, and we don't want to change that. So we are just adding essentially a little component that creates an isotropy. That's all we want.
Okay, so basically, if I think of how to implement this experimentally, you rotate the sample and simultaneously increase the magnetic field in your coil.
I think, but I'm not sure if that's actually going to be doable in a real solid state system. There are other ideas. The original idea due to Kuhn-Young was actually just to do like a acoustic wave type experiment, which is probably much more realistic in that case. One thing that, the main problem with both of these ideas is, can you really see these dynamics in the time scales that you can actually measure in a solid state system, which has phonons and all other kinds of crap? So I don't know, maybe at this point it's not so easy because, if you plug in the time scales due to the magnetic length that you have in gallium arsenide, it's probably very, very small time scales that you need to resolve. If you go to like a lattice system or maybe even graphene, something like this, then the timescales become much more favorable. So if you're in a lattice system, you could have timescales which are basically microseconds. And that's the kind of timescales that, at least in cold atoms, that's what people measure these days easily.
But this is actually closely related to the second question I wanted to ask. So basically, how fast do you need to rotate your sample? So, and that's the first half of that question. And second, if you come back to thinking about rotating the magnetic field, inevitably that generates some electric field. So
no. Sorry, I want to clarify. We don't want to keep rotating. What we want is we just want to fast add a component of parallel field.
Okay.
And you want to do this as fast as you can. So you don't want to kind of keep rotating.
Okay, but this creates an electric field. So what would that do?
Well, the electric field shouldn't affect the graviton dynamics because it's a spin-2 thing. So as long as you can suppress the gradient of the field to be sufficiently low, you should be fine.
But the field is proportional to the frequency. So the faster you add your parallel field, the higher is the electric field. So my concern is that you will just have the breakdown of quantum Hall effect or some other undesirable things if it's too fast. So there must be some limit.
Yeah, one would probably have to look at the numbers and make sure that, you find some range where you shouldn't do that.
Okay, thank you.
I think the next person with their hand up was Zong. Zong, are you there?
Hi, Papic. I have one question for you. You show that you have the spin 4 excitation here. Is this correct?
Yeah.
Can you think of the spin 4 as a combination of two spin 2?
Well, I don't think the energy at which it appears is not just the double of this.
No, because you can have the interaction between if you have the bounding of two spin 2, can you have the spin 4?
I think they might be different. You will certainly get the bound state of two spin 2, but I think there is also a contribution of a genuine spin 4.
how can you distinguish these two situations?
Because if you look at this spectral function
Yeah.
for this octupolar one,
Yeah.
then it doesn't, I think, have only one peak at high energies. There's like a doublet of peaks. So it's a bit similar to the bilayer case, where if you look at the spectral function, so I didn't show that, but so this is the spectral function for the bilayer, where there's like a bilayer spin 2, and then you also have the spin 1 cross spin 1, and they have two distinct peaks. So I think something similar is going to happen also in the single layer with spin 2 and spin 4.
So in your experiment, in your numeric, you see another peak of the 2 spin 2, or you only see the spin 4?
We see two, I think, two peaks. I mean, it's been a while since I looked at this, but I think we saw two peaks at much higher energy than the graviton. And yeah, one of them was like really double the energy of the graviton, and then the other one was some other energy.
Okay, thank you.
Eduardo?
Yes, this is a question for Zlatko. This was a really nice talk. Can you hear me, by the way?
Yes.
Okay. I have a question about the non-abelian quantum Hall effect. And as you probably know experimentally, we now know that there is a proximate nematic state to the phi-half state by, say, applying hydrostatic pressure or by tilting. But mostly the interesting case, I think, is the hydrostatic pressure because in principle doesn't break any symmetry. So there's always been a question about, I mean, when you have two states which are in close proximity, you may wonder if they may have a common origin. That microscopically, the Hamiltonian may want both. The nematic state can be viewed as a condensate of this quadrupolar mode. And there is a question whether such a mode exists inside the phi-half state. I think the current experimental evidence, at least, I don't know, I think Aaron Pinsock might talk about that later. I don't think they see it inside the phi-half state. But there is a question whether or not, what is the role of the GMP type mode in the phi-half state? I don't think this is a well understood problem.
I'm quite surprised that they wouldn't see it because the GMP mode should basically be present in any kind of gap.
Yeah, I know, I understand, but they don't seem to see it.
I mean, certainly in numerics, like here,
yes,
this is the GMP mode, and that's like a neutral fermion, so you definitely see both modes.
Can you, doing your simulations, apply the analog of hydrostatic pressure and see what is the effect of this?
Well, if you tell me how to model it, I can apply it, but I don't know how to model the pressure.
Well, you can, yeah, sure, you can model the pressure in the...
I mean, I haven't really thought about it, but so this case that I'm showing here, this is a sort of nematic phase at 1/3.
Yes.
This is the paper by Nicholas. Well, similar model that was by Nicholas and others.
Yes.
So there it looks sort of like what you expect. I don't have any data for phi-half. I'm not sure if we can see something as nice as that in those cases.
Okay. Well, that would be very interesting to explore, in fact. But,
yeah.
Okay. Beautiful talk.
Thank you.
Next is Bo.
Oh, hi. I have two questions for Zlatko. The first one is actually sort of related to what Dima was asking. So what you're doing here is a quench when you just suddenly apply an in-plane magnetic field, right? Right? Just okay. So in that case, even if there is an electrical field, it's a very short. You just have an electric field for a very, very short period of time. You don't really have an electric field in your system, I suppose. After you do the quench, so before T, you have the out of plane magnetic field after.
Yeah, but the problem is, I guess, if you really apply it for a short time, it's going to have a big gradient, right?
Right, but it's a strong electrical field for a very short period of time. It won't affect any dynamics, right?
Well,
so after that, it's a constant Hamiltonian. I just want to clarify, it's a constant Hamiltonian after the crash.
Yes.
Okay, so then in that case, we don't have to worry about the electrical field, I suppose.
Can I comment on this? Experimentally, what they do is they don't tilt the field, they tilt the sample and they increase the field to compensate so as to keep the normal component fixed.
Right.
So in that case, the only thing you're changing is the normal component of the magnetic field, and you're tilting, physically, you're tilting the sample. That shouldn't produce any, well, there could be an electric field because you're changing the magnetic field, but this is the same as when they sweep in magnetic field.
Right, when you're tilting it, you create an electrical field, but after you finish the tilting, you stay there and let the thing evolve. And then the Hamiltonian is time independent. And I suppose there's no electrical field after that.
I think there is a presumption of adiabaticity.
Well, not in the numerics. I mean, the numerics is really you just at time t equals 0, you're in the ground state of isotropic Hamiltonian. And then immediately after that, you just turn on another Hamiltonian, and then it's a static Hamiltonian, and you just do Schrödinger time evolution after that.
Right. Okay. I just want to. So the second question is something actually I think I asked you before, but I can't remember the answer. So the graviton mode is actually in the quantum sector of non-zero momentum, right? Even in the thermodynamic limit approaches 0, but it's not really in the Q equals to 0 sector. So when you are doing the quench, I suppose you're only coupling the ground state to all the excitations in the Q equals to 0 sector.
Yeah, that's a very good point. So the technical point is that because we do not break translational symmetry during this quench, and we start from the ground state, which has 0 momentum, we stay in that 0 momentum at every time after that. Right. So that's kind of interesting that we actually see anything, because as you said, when we construct the graviton mode, it's actually, an L equal 2 sector, but that still has, some kind of projection, because the quench actually breaks L square invariance on the sphere. So you allow it to couple it with other states.
You're doing it on the torus, I suppose.
We are doing it on a torus, but it's easier to think about the sphere.
But it's a linear momentum sector, right?
I mean, on a sphere, let's talk about. I mean, you have angular momentum too, right?
Yeah, but you have degeneracy, so any linear combination of to give you the linear momentum as well.
Yes.
So I think it's very interesting because the effective theory agrees with the numerics very well. So you definitely see this kind of oscillation related to the graviton mode. But in the Q equals to 0 sector, so a related question is, how do you distinguish the graviton mode with, for example, 2 dipole moments arranged in a way with a quadrupole moment? That you can do, right? And it can happen in the Q equals to 0 sector.
It can happen, but it doesn't seem to happen. And that's probably related to some inversion symmetry or something like this.
Okay.
Is maintained here. So we don't actually have a spin 1 excitation.
Okay, I see. The energy is close because it's like 2 times the Graviton minimum. But you're saying that when you look at the spectral function, you don't see that.
No.
I see. Okay, that's interesting.
Jainendra?
Yeah, I have a couple of questions. One is, so I'm looking at this higher spin mode. So within composite fermion theory, the lowest mode can be described in terms of excitation by 1 composite fermion lambda level. But there are higher energy modes where you excite a composite fermion by 2 or 3 or more lambda levels. So there is also experimental evidence for those from Aaron Pingsuk's experiments. So the first mode occurs at L equals 2, the second, there should be a mode at L equals 3 as well. Do you see, I mean, is there
no, we don't see the odd ones. I think probably something related to inversion symmetry, but I'm not completely sure. But we definitely do not see the odd ones.
Okay, but within microscopic theory, one can check whether these higher spin modes do actually correspond to excitations of composite fermions by more than one lambda level. That's something you haven't tested, correct?
No.
Okay, my second question was, so for Laughlin states, the collective mode in the long wavelength limit goes into the continuum. But that's not true for other fractional Hall states like 2/5, 3/7, or the bosonic analogs of those. Is there something, so does it lead to some complications or simplifications?
That's just going to make it better, if anything, because if you're below the continuum, then it should be much easier to excite it and get something coherent.
Okay.
The real difficulty is when you're buried in the continuum and you have like a density of states into which you can scatter.
Okay. So maybe it would be interesting to look at other fractions because there the collective mode does not go into the continuum in the long wavelength limit. So
that's actually a very good question. I think there isn't really any understanding of this, but it would be really nice to understand how you can actually move that mode as you want, right? How can you
change pseudo potentials? I think it's just a matter of pseudo potential.
But it's a very nonlinear thing. I mean, I don't think there is any real recipe, right? It requires a lot of experimentation and.
Cool. Okay, thank you.
Any other questions?
Okay, so hello everyone. So I'm Ken Ma, and I will be